Hey, all right, so we're going to continue and talk about local maxes and mins. Um, and these are going to be what you think they are. It's when a function hits a maximum or hits a minimum. So let's draw another graph. A function, we can draw another bike riding function. This time it's going to be a little bit more sporadic. So this looks something closer to the runs that I go on, where I tend to do a lot of loops. So if we're looking at distance from home, we would start again at 0, 0, and we end at, that could be, maybe let's make that 60, 0. So we went for 1 hour. And a function has some local maxes. So these 2 points right here are local maxes. That means that the function has hit a peak. So it's when you're increasing, it's the point where you stop increasing and you start decreasing. So when you transition from increasing to decreasing. And we need this definition of a function has a local max if it transitions from increasing to decreasing. Because we just actually need terminology to say what we're talking about. When we're looking at a graph, we usually think of local maxes as just the tops of peaks on the graph, but that definition, it doesn't hold for all functions that well, or it's not that clear. So this gives us a clear way to classify if a function has a local max, and has a local max if it's shifting from increasing to decreasing. So it's going up and then it's going down. And likewise, we have a local min. And we have a local min if we go from decreasing to increasing. So they're complementary concepts. You have one, and then you can kind of figure out the other. And so what would be happening here is that maybe we're running for a decent amount of time, and then we turn around and run in the other direction for a little bit, and then turn around again and run in a different direction. So the distance, so we hit like a local min when it's like, oh, we're like pretty close. Like we've gone from getting close to something and then going back away from it. And so as an example, here we're just going to draw a graph. So one problem that we might see in classes or homework or on an exam is a graph that looks like this. It'll have some points labeled. Oops. Data 15. And it'll ask you to find all x where f of x, label our axis, we know that's f of x, is a local max. And then we would look at our graph, and we would know that a local max is wherever we're at the top of a peak. So we've increased, and now we're decreasing. So x equals 5 is a local max. And now pause the video. There's only one other local max. And think about where that max is. And so that max will be at 8. And then find all local min. I'll let you guys tackle this one. So just take a second to pause the video and think about where all the local mins are. So hopefully you found that the local mins are at x equals 7 and x equals 9, because that's where we've decreased and shift to increasing. We've decreased and shift to increasing. And that's about all there is to it to local maxes and mins. In future videos, we'll talk, or future sections and chapters, we talk about optimization, where we're interested in finding these maxes or mins, where maybe the graph represents costs, so we're interested in minimizing cost. The graph might represent profit, so we're interested in maximizing profit. Usually we just stick to economics problems, but there's a whole range of questions out there that are interested in optimizing a function, finding a local max or a min. They're just harder to state. A lot of machine learning and artificial intelligence actually focuses on trying to maximize a function that tells you whether something is true or not. And that way a machine can make a decision from that. There's a whole bunch of computer scientists out there that do work in this optimization to determine where the local maxes and mins are. The final concept is absolute max and min. And the absolute max or min implies that we're looking for the best one. So the largest max or the smallest min. So this is where the function's at its absolute greatest or absolute least. So we can draw a function like we had before. And I'm going to change it just a little bit. So now we're not starting at 0. All right, so take a second to think about what the values are for the local maxes. So hopefully you found that the local maxes occur at those two peaks, so at 10 and 15. And maybe we can say that that's x equals 7 and x equals 14. Also over here at, let's call that 21, just for symmetry. And that's not a local max, that's just an endpoint. So for the absolute max, we look at our local maxes and our endpoints. So the endpoints are important, where if our graph ends, then that can be a local max, that can be an absolute max as well. So we have our endpoints. At our endpoints, our function is either 5 on the left or 20 on the right. And our local maxes are 10 and 15. So the absolute max is actually 20. It's that endpoint value. If we're looking for the absolute min, take a second and see if you can identify the point on the graph that is the absolute min. Yeah, so we would just look at the endpoints and look at the local mins. So we have local mins here, 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 and we can see that both of our endpoints are bigger than this point. So this point is our absolute min. And if we wanted to, we could assign values, maybe make that like 4,2 or something. It doesn't really matter. All right. I think it'd just be a good idea to try and look at a lot of graphs and identify absolute maxes and mins, as well as local maxes and mins for those. These are something that once you do several times, you can get pretty comfortable with and becomes almost immediate. All right, I hope you enjoyed.